So if you're here, thank you. Not many people by week 8 have rocked up to the 9 a.m. class because, of course, we don't have mandatory attendance. So this generally is how it goes. So hopefully you all did pretty well in your midterm. The results, I believe, will be coming next workshop. It'll be a similar process where they're still marking it right now. Maybe you can expect towards the start of next week to get the online mark back, and you can check on Moodle and all that for your grade. And then we'll be given the actual papers just before next week's workshop, and you can come collect it. So yeah, hopefully that was all good. I'll come around the mid workshop break, and just come around and ask you guys, how you went, and like if you've got any questions to do with that test, etc. But anyway, so this week we're going to talk about particle kinetics, and this is building on from kind of the stuff we were doing last week. I wasn't here last week, so if you came, surprise, I was unavailable on that Thursday, so there was someone else covering. Anyway, so in terms of where we're at in the course structure, we're well and truly into the dynamics portion of the course. We're going to talk about particle dynamics first, followed by dynamics for rigid bodies, which will be next week. And spoiler alert, that will be the hardest topic that you're going to see in this course. So next week's workshop, you can expect it to be relatively hard. But this week's workshop's relatively straightforward, I want to say. It will be building off of a lot of the stuff that you've probably already become familiar with throughout your high school physics and physics 1A from last term. Okay, so in terms of kinetics, we can break it down a bit further. The three kind of overarching topics we're going to be talking about today are going to be using the equation of motion, which is Newton's second law, F equals ma. Using work energy methods, so I'll explain what that means a bit more later, but it's just equating the work with the sum of different changes of energy. And similarly, we've got impulse-momentum relationship, impulse being the change in momentum. And yeah, okay. So before we get into anything, I just want to kind of break down a few concepts which you'll start to see in the next few weeks. And one of them is pulleys. So pulleys are kind of like, it's where you've got rope involved and you've got this kind of wheel thingy that is free to spin around an axis. And we assume that these pulleys are massless and frictionless, but you're going to see a few different types of pulleys. So you can kind of break it down into passive and motorized. We're not really going to be touching the motorized pulleys in this course, but if you're like a mechanical engineer, for example, you might see this in the following courses. So in this course, we're just focused on fixed and movable pulleys, and these are the ones that we want to be able to differentiate between. So a fixed pulley, the way that it works is generally you've got one continuous rope that runs through it, and the rule of thumb you can think of is whenever you've got one piece of rope that's continuous, the tension in that rope is consistent. Okay, so whatever tension is, whatever tension force is in the rope in this part is going to be the same tension force that's on the part over here. And what happens is this tension is redirected at the fixed pulley, and it's balanced out in equilibrium by the reactions, okay, of the fixed pulley. So the pulley will be on some kind of support. Let's say it's a pin support. And the pin support will have these kind of reaction forces that puts the system in equilibrium. However, we're usually not concerned with what those reaction forces are. So for the purposes of all these questions that you're going to be doing in this course, we don't need to find the reaction forces. That's not what we're interested in. You just need to know that the support will do its job in redirecting the tension forces. Okay, and then the other type of pulley that you'll see is a movable pulley. So in this particular movable pulley, example that I'm showing you here, you've got also a system at equilibrium, except you've got two ropes, okay? So you've got one continuous rope, as I've highlighted in green, and then you've got a separate rope, which I've highlighted in yellow, okay? So these ropes are kind of attached to different points in this pulley, and the same rule applies. So whenever you've got a continuous rope, it's got the same tension force throughout it. Okay, so for this system to be balanced in equilibrium, essentially there has to be equal amounts of force going up and down, and therefore the rope that's highlighted in yellow actually has twice the amount of tension as the rope that's been highlighted in green, because the system has to be in equilibrium. So what this kind of results in is this idea of a mechanical advantage system. So when you've got like two or more ropes like attached at these movable pulleys, they can multiply the amount of tension that's, I guess, yeah, so there's different ropes, and then one rope can have twice the amount of tension as the other rope, okay? So I'll give you an example to better explain it, because that was kind of a poor explanation. Okay. Essentially, with mechanical advantage, you're trading off force for displacement, okay? So what do I mean? Let's do an example, okay? So here we've got, let's say, some kind of external force on the system. Let's say this is my hand, and it's pulling the rope going that way. You've got a fixed pulley here, and we know that a fixed pulley cannot generate mechanical advantage, okay? So this is simply redirecting the tension force. So what we can do is, if we break this down in terms of the individual free body diagrams, right? So this free body diagram would look something like this, right? You've got the weight force, and then you've got the tension force. Let's call that T. So if you do some of the forces being in equilibrium, you'll find that T is equal to mg. And if you do this free body analysis here, you'll find, I'm just gonna, oh, actually, running out of space. Let's just quickly draw it here. This is kind of overkill what I'm doing, by the way, but I'm just trying to explain it thoroughly. You've got the rope, and you've got your reactions that are redirecting the tension force. So T over here is T over here, and the reactions balance it out, okay? And then finally over here, if you wanted to do this as like a very thorough free body analysis, free body diagram analysis, right? Get the dude's hand, and that's the force that's applied, and the tension force in the rope, right? And we know that these two things will be equal as well. Okay, that's all just to say that you can, that the amount of force you're applying, right, is going to be equal to this. I can't be bothered to do the maths. Give me 1 sec. I forgot to get my notes up. Week 8. Okay, yeah, sorry. I'm gonna do it in kilonewtons, okay? So yeah, anyway, this is just a very long way to say that this is the force in the rope, okay? So yeah, we've got a mechanical advantage of 1. However, if we introduce a movable pulley into the system, let me just erase these highlights for a second. You'll see that we've got one continuous rope that coils around these pulleys like so. So this pulley is fixed, and this pulley is a movable pulley, right? And this can allow for a mechanical advantage of 2. Okay, so let's follow the same logic. So if we did the free body analysis here, this is mg, and let's call that force T that goes into that rope, the blue one. Okay, and so if we do the free body analysis here, let's keep calling that force in the blue rope as T. If we did equilibrium analysis, you'll find that each of the forces in the red rope is going to be T on 2. So all of these upwards arrows, that are in red have to match the downwards arrow that's in blue. And essentially this is all to say that the force in the rope is going to be T on 2, okay? So this basically, it gets halved. Okay, so what does this mean? It means that if I'm pulling on this rope, I only have to pull it half as hard as I did when there was only a mechanical advantage of 1. But the trade-off is I need to pull it twice as far, okay? So in terms of displacement, okay, if I want to just hold the box still so it doesn't move, all right, the rope will pull my hand in that direction with a force of T on 2. If I wanted to apply a force to move it, I only need to apply half the amount of force as I would have without the mechanical advantage system. But I need to pull it twice as far. That's what I'm trying to say. Does that kind of make sense? So that's kind of how mechanical advantage works in terms of pulleys and ropes. Okay, so I just want to explain that first before we got into our first question. So this question has like a few different components to it, right? The first thing is the pulleys that I briefly described. And the second thing is friction, okay? So in the very first workshop, I briefly touched on how friction works, but we were still talking about it in terms of statics. And if you recall for that question, it looks something like this. I'll just quickly draw it out. So just to give you a recap on friction. Okay, so there's a force, and you know the angle that, let's say this is a rope or something. You know that, and let's say this is like a hand that's pulling it. Yeah, like there's a hand that's pulling this box, which is attached to a rope with a force of F equals whatever. And then we know the material properties of the ground. Let's say these were the numbers. So these are the coefficients of static and kinetic friction. And essentially the way that you had to analyze this question was you compare the weight and the normal force, and then you can find the friction. So the friction is resistive to the direction of motion. Okay, so that's kind of how it worked. But in terms of what we knew about it back then in terms of statics, right? Actually, you might not have even seen the kinetic friction constant before. The idea is that you've got this number called the static friction coefficient, and you can find something called Fs max, all right? And that's the static friction threshold. So Fs max is equal to the static friction coefficient multiplied by the normal force. And this gives you some number. Let's just say for the sake of argument, it's 100 newtons, okay? So this is the threshold number of friction that can resist a pulling force before it starts to move. Before it moves, okay? So if you think of it like a bucket, all right, I'm just going to use a bit of a different analogy. So there's a bucket that can hold water. The capacity of the bucket is your threshold. And if we were to fill up the bucket with water, and in this analogy, that just means you're pulling on the rope harder and harder, at some point the bucket overflows, okay? And once it overflows, your system starts to move, okay? So that's kind of what you have to think about, right? So hopefully that'll make more sense as we do the question. We're just going to do that, except we're going to add on the layer of complexity, which comes from there being pulleys, okay? So in this question, we've got a fixed pulley over here, and we've got a moving pulley over here, okay? So we're interested essentially in this free body diagram of the box and the associated friction. I should draw the friction down here because it's more accurate. Yeah, so we're interested in that. And what we have to do is we have to calculate the static friction threshold and check if the box is actually moving or not, right? Because we don't actually know if this amount of tension is going to cause the box to move. So we're going to have to compare that. And then if it does move, then we launch into kind of our equations of motion and figure out how fast the box is moving. So we're interested in finding the acceleration if the box is moving. Okay, so as I mentioned earlier, you've got the tension in this rope, and it's a continuous rope, right? But you've actually got a mechanical advantage system built into it because you've got basically two parts of the rope that are pulling with a tension force of 100 newtons at this free body diagram of the box, right? So you've actually got two lots of 100 newtons pulling the box that way. Yeah. So, so we're going to do static analysis first, okay? So the first thing we do is we draw this free body diagram. We can calculate the weight force through m times g. We're given what the mass of the box is. And we also know that we've got two lots of tension pointed at 30 degrees from the incline, at an angle of 30 degrees from the horizontal, inclined at 30 degrees from the horizontal. And we've also got the normal force. So when we're doing these questions, we always have to find the normal force first before we find friction, because friction is dependent on normal force. Okay, so we do some of the forces in the direction of the normal force, right? Which in this case is going to be upwards because the ground is flat. Okay, so if we do some of the forces in the y direction, we get the normal force pointed upwards like so. And we have to do two lots of the vertical component of the diagonal force, right? So using our understanding of force components, we are going to add on two lots of 100 newtons, and we're going to do sine 30. Sine 30 meaning if we look at this like a right angle triangle, we're looking for the opposite side length, right? Okay, and then we subtract this by the downwards arrow. So the downwards arrow is this one, right? So we're going to subtract the weight, which is mg. So it's this, which I've already pre-calculated as 392.4. So you can rearrange this expression now for n, which is the normal force, and you get 292.4 newtons. So that was step one, finding the normal force. Okay, next we're going to look at the horizontal forces, right? So we're going to take the horizontal equilibrium, okay? And let me just redraw some of those arrows. So now we're interested in two lots of the horizontal component of the diagonals, and we're also interested in the friction, okay? So we're going to add the red arrows pointing to the right, and that's two lots of 100, and now we're doing cosine 30 because we have the adjacent side of that right angle triangle, right? And then we subtract off FF. So FF is like theoretical friction that's applied, okay? So this is the applied friction if the box was completely still, okay? So that's 173.2 newtons. Okay, so now what we have to do is we have to check this number. So this is the applied friction. And we have to check that against the static friction threshold, right? So to find that, we get the static friction coefficient, which we're given as 0.5. Chuck in 0.5. And we multiply that by the normal force, right? Which was what we got from step one, giving us 146.2 newtons, okay? So this is your capacity. Okay, so why was I talking about the bucket earlier, right? So if you imagine that your bucket has a volume, and that volume is this number, 146.2, right? And if you imagine the water that's in the bucket being the applied value, right? 173.2. If you compare these two numbers, you can obviously tell that the bucket is going to overflow, right? Because 173 is bigger than 146, right? So if the bucket overflows, our system's actually going to be moving, okay? So that's what we're saying here. Since 173.2 is greater than 146.2, we have to use the kinetic friction value and use the equation of motion, okay? So equation of motion, there's kind of two sides to this, okay? First, we sum the forces and we point the arrow, right? So in the statics portion of this course, we were always pointing the sum of the forces to the right when we did horizontal equilibrium, and we were always pointing the sum of the forces going up when we're doing vertical equilibrium, right? But for dynamics, it's more useful for us to point it in the direction of motion. Okay, so we know that physically, if the box were to move, it's going to move to the right. Okay, which just happens to be the same as what we would do in the statics portion of the course anyway, in this particular case. But if, for example, the box was going to move to the left, it'd be better for you to take the positive direction as going to the left in that case. Okay. Anyway, so you got this part and you got this part. Okay, so we're going to look at the green part first. So we're going to sum all the forces, right? So taking right as positive, okay, we've got, again, two lots of the red arrow, okay? So we're going to just copy that over from before. Except instead of subtracting by FF, this time we're going to subtract by FK, okay? So FK is a new number, okay? It's mu K times normal force, okay? So the reason this is different is because we've got a different number for the coefficient of friction when the system's moving. Usually this is lower than the static one, okay? So this is 0.4 instead of 0.5. And we multiply it by the same normal force that we had before. And we get 116.96, right? And so if we were to sum all of these things, oh, actually, okay, no, sorry, let's not do that yet. My point is, if I highlight this, right, there's kind of 2 points, there's kind of two parts to this equation. You've got the green stuff and then the yellow stuff. So the yellow stuff we have to also kind of consider, okay? So we know the mass of the box is 40, except what the question wants us to answer with is acceleration, right? So what we're going to do is we're going to get the green part of this equation and we're just going to divide it by 40, and that will give us the acceleration, right? So the acceleration is 1.406 meters per second squared, and that's going to the right. So that's your final answer. Okay. Hopefully that made sense. So what you'll notice about rolling friction or kinetic friction is that it's a flat number. Okay. So here's a little graph, right? And this is saying this is the amount of friction on the y-axis, and on the x-axis, you've got the applied friction. Okay, so this is not a super intuitive graph at the start, but I'll explain what it means. So in this first portion of the graph, what it's saying is that the friction when your box is not moving matches your applied force as if it was like a reaction, okay? Up until the static threshold, which is this number, which remember, this was 0.5, and then it drops, okay? It drops to 0.4 of that, and then it's constant. So now this is, now when the system is moving, kinetic friction is a flat number that constantly opposes the direction of motion, as long as the box is moving, right? So this is a force that is always opposing the direction of motion. Does that make sense? Does anyone have any questions about that? So that's friction, that's pulleys, and that's Newton's second law. Okay, so what I'm going to do is I'm going to run through this page of theory and this page of theory, it's related to springs and energy. And then before we move on to question 2, I'll just give you guys a break, okay? So we're just going to go through some theory first. Okay, so in this workshop, I just want to make some notation clear. Your letters will represent different objects. So for example, if we've got a car, we've got 2 cars rather. All right. If I say A and B, it's just referring to different cars. Okay. If I say 1, 2, or 3, this is going to represent different states of energy. You can also maybe think of this like different states of time. Okay. So for example, these 2 cars at the start in state 1 are moving together, like into each other as if they're about to crash. And then let's say that they rebound off each other. So you've got the 2 cars, and now they're going to bounce away from each other. So this is now state 2. Okay, so state just refers to different points in time or different points of energy. Okay, you can think of it either way. Yeah, so that's the notation I'm going to use for the rest of the workshop, rest of the questions, the rest of the formulas, right? Okay, let's talk about springs. So a spring will be usually like a coil made out of steel or some other metal, and it's got this undeformed length, which is called its equilibrium length. This is basically the length which it wants to be at so that it doesn't feel the need to oscillate. So if you squash the spring based on this undeformed length, it's going to want to return to equilibrium, and it's going to want to push back to get back to the undeformed length, right? Similarly, if you pull the spring and elongate it, it's going to want to return back to equilibrium and get back to the undeformed length as well, okay, in tension. So, yeah, you can draw out a spring material curve. This isn't quite a material curve because a material curve is usually stress on the y-axis and strain on the x-axis, except you can kind of think of it like similarly. So on this particular graph, on the y-axis we've got force, so the applied force, and on the x-axis you've got instead of applied force, you just think of this like spring force. And on the x-axis, you've got the length of the spring. Okay, so there's kind of 2 formulas that you can visualize on this graph, right? The first one's Hooke's law, and this is just saying that there's a linear proportionality between the force in the spring and the length of the spring, or like how much it's deformed, and that proportionality is K. So that's called the spring stiffness, all right? So yeah, so this kind of number embodies like the spring's geometric property. Actually, let's just call it shape, just for simplicity. The spring's shape and the spring's material, okay? This is just an all-in-one number, which represents these 2 things, okay? Okay, and then spring energy is basically the potential energy that the spring has based on how much it's deformed, okay? So it has 0 potential energy if the spring is undeformed, okay? But once you press it in and compress it, or once you pull it out and elongate it, it now has potential energy, right? And the potential energy is the energy that it wants to return to equilibrium with, okay? The equilibrium length with. Okay, so if that made no sense, that's fine. It might make more sense like in an equation, in a question rather. Okay, and speaking of the deformation length, right? So what I'm trying to say is this is the deformation length. So if you elongate a spring based on like relative to its equilibrium length, right? Or if you squash it, that's the potential energy that it has. Oh, sorry, that's not the potential energy it has, but that will inform you about how much potential energy it has, right? So how far off it is from equilibrium. And there's different notation for it. Sometimes you'll see it as delta L. I think in some of the working out that I do in this workshop, you might see it as X. So X is just referring to, for example, delta L1 means based on the energy state 1, this is how long the spring currently is. This is its equilibrium length. And so this is how much it's deviated from the equilibrium length in state 1. Okay, and then in state 2, this is how long how long it is in state 2. And this is its equilibrium length. And so this is how much it's deviated from the equilibrium length, right? So that's represented by X. Okay, next is work energy. So you may have seen this formula in physics and whatever, but you may have seen it represented by different letters. So in this workshop and in my class, these will be the variable names. Okay, so W stands for work, and it's the work done from state 1 to 2. So work is the change in energy, right? So you need 2 reference points, right? The first state and the second state in time or energy. Okay, and then it's the sum of these different components, okay? The first component is kinetic energy, and kinetic energy is basically the motion. It's based on the energy due to motion of the object. And the second one is gravitational potential energy, which is based on how much energy it could potentially add to the system because it's been like elevated from a datum. And then the spring potential energy is how much potential energy it has because a spring which is attached to your object has deviated from equilibrium. But it doesn't have to be attached to your object, but you'll see what I mean as well. So these 2 types are potential energy types, okay? All right, so we can actually break down all of these components further, right? So work has a formula, and it's the force multiplied by the change in displacement. So I think there's a dx something missing that. So this is the discrete version. This is the calculus version. Anyway, so F is representing the external force in the system. So this can kind of manifest in 2 ways. The first one is if someone is pulling on a rope, for example, this is adding energy to the system. And the amount that the rope has moved is going to be that displacement value that you're interested in. Okay, and then the second case is, say, friction that's removing energy from the system. And in that case, S will be representing how far along it's slid. Okay, so for example, got a box and it's on this rough ground with friction. Okay, and you're pulling rope. Okay, so that's a pulling force. But the idea is that let's say that box moves some amount of distance, right? So from there to there is how far it's moved. That distance is going to be the displacement, and the kinetic friction is going to be F. So that's how much energy has been removed due to friction in that particular scenario. Okay, and then we can break down kinetic energy, gravitational potential energy, and spring potential energy into these formulas, right? Which I think you might be relatively familiar with these ones already from physics. You might not have seen the spring potential energy formula before, but that's okay. We'll see it in the upcoming question, all right? Okay, so that's the question, except what I'll do is I'll give you guys a break. So I'll just say break until, let's give you guys 10 minutes, so 9:55, and I'll just come around and yeah, you can just ask me any questions you might have about, say, the assignment or like your quiz or anything like that you had, or the upcoming one. Yeah, I'll come around. How did you find the test? Yeah. I've heard that before as well.
I don't have time for that submission.
Yeah.
I tried to, like, after I walked out of the exam, I realized I couldn't have done the last question easily.
Oh, that's okay. I think frames probably one of the hardest topics. force. So it's quite time consuming.
I found frames easier than the joints.
Oh,
Like in sections. Frames are special.
oh,
Easier than the second
Trusses, sorry.
for the second version. I like. I'm just saying.
no, like, it might be available on Moodle, but I have no chance.
Are you able to use both sections and joints for the same question?
Yes.
Okay. Nice.
It doesn't matter which one you choose for the sections of joints. They're equivalent because all they're doing is finding the member's internal force, whether it's tension or compression. It's just when you choose one method over another, the advantage comes from like how quickly you can find the answer. And some applications are better than others based on the question.
The way they asked the question was like they had like the three. They wanted us to find four, like four of the forces. Like there was three going down a truss, and then there was like one like separated by itself, like far right. So I just did like joints for that part.
Oh, that's fine.
Is that you can do
Yeah, you can absolutely mismatch them. Yes, as long like they're interested in getting correct final answer for the customers should get. Yeah. So if you're able to mismatch, just do it correctly, that's 4 months. Yeah. But you'll get your mark back probably, like you get the grade probably like start of next week on Moodle sometime. And then you get the paper back with the next one, sure.
What if you want to pass if you've already got some first one?
I think all three of these exams in average of over 40%. So probably that's- so between the first, second, and the third is the average mark that you got in the list is above 40.
But this wasn't the way to move. So
Oh, true. I don't know how that works. It's maybe potentially. Yeah, yeah. That's a great question. This is the first time we've run also this week, so I'm not too sure. Yeah. Next. Any questions? Oh, just in general. Oh, do you have any questions about the course? Okay. That's actually. Do you have any questions? Sorry. Oh, yes. That's fine. Yes. Good question. Do you mind if I ask a question after the workshop? Yeah, if you've got time. That's probably easier for the summary related questions. Yes. Yeah. So one of these should be given to you. Yeah, that one's given to you. The allowance stress. The other one is relationship. Stress is equal to force over area. So you find the max force in all the truss members. And then you divide it by the sectional area. It'll be all the dead loads on top of the impact force in the seconds analysis. Yeah, you use together. So, the static case. So I'm just drawing the top part of the truss. You'll do 1, 2, 3, right?
Yeah.
For dynamic. You'll do 1, 2, 3, as well as the impacts. So don't just do that one by itself. You still need the loads and you have impacts. What I do? Do you have any questions? You can do it on the computer. Yeah. Yeah, either way, as long as you present like you know how my notes are digital. Like I can basically upload one of the pages of my work on this yeah, like when they say by hand, it just means step by step working out. So that like a computer analyzing what information is in like
Very detailed.
as detailed as all the questions and as detailed as what you might put in like a quiz. So just be reasonable. Like as long as the marker can read it and follow along with what you're doing. That's the real detail that's expected. Thank you. So what's the letter G? Do you have any questions? Probably next week. Wait, 6, 7 next week. Oh, yeah, I think week 5 I might have done that. Yeah. If you haven't collected it yet, just send an email away. Because he has all the leftover papers on his desk. So if I'm looking at it, yeah, we've given it back to him. Any other questions? All right. Let's continue. Cool. Let's do question 2. So this is what it looks like. Let's get it up on my phone. Okay. So what's going on with this question? Okay, I'll explain how the system works. Let me just erase this stuff that I've drawn on it for now. So the idea is you've got this, it's called a collar, and it can slide along this shaft up and down. And you've got a pulling force. I think the force that's on it has been cropped out. And you know these dimensions, okay? So you know there's a 450 mil distance between the center of the collar and the edge of the spring. And there's a 225 mil distance between the center of the shaft and the center of the fixed pulley B. Okay, so if we read the question, it says a 7 kilogram collar A slides with negligible friction on a fixed vertical shaft. When the collar is released from rest at the bottom position as shown, it moves up the shaft under the action of a constant force of 200 newtons applied to the cable. What we want to do is we want to find the stiffness of this spring using like conservation of energy basically. And an additional bit of information we're given is that the max compression in this spring is limited to 75 mil. So if you think about it, this, I guess like from the middle of this collar to the edge of this collar is 75. So a spring can only be compressed that amount, right? So if I redraw what I rubbed out before, the idea is we're going to analyze two states of energy. The first state of energy is the starting position. And in the starting position, a couple of things, like we can consider a couple of things, okay? Firstly, the rope, right? We can actually measure this distance of the rope, right, in state 1, okay, using Pythagoras, right? So it's a right angle triangle, and we can look at the hypotenuse of this right angle triangle, giving us the distance between A to B. Okay, I'll tell you why this is useful later. Okay, and then in state 1, the spring is uncompressed. We're not touching the spring. Okay, and then in state 2, the collar slides up and the system stops moving because the spring kind of opposes the motion, and there's no more kind of vertical force because the rope is going to be completely horizontal at that point. Okay, but now we've got spring potential energy essentially because the spring is going to be partially compressed. Okay, and then so what you'll notice as well about this system is in position 1, let's just pretend this is where the rope ends, right? As the collar slides up the shaft, what's going to happen is the rope's actually going to elongate, right? Well, not elongate, it stays the same length, but it's going to move along the pulley, okay? So how are we going to essentially measure how much the rope has moved from the end, from position 1, from state of energy 1 to state of energy 2? Okay, and the answer is by taking the difference between what the rope was measured at between A to B and what the rope is measured at between A to B in state 2. Okay, so comparing state 1 to state 2. So what you can see is that the amount that the rope shrinks, right? So let me do it in, let's say, blue. So in state 1, okay, versus state 2, between A to B, the rope has shrunk, okay? And that amount of shrink is the elongation on the other side, okay? Does that make sense? So what we're interested in is this, because this is going to be our displacement for the amount the rope has moved in the work part of our equation, okay? So that's what we're going to need to do. We're going to analyze the geometry. So let's call the hypotenuse, right? We're looking at state of energy 1. Let's call the hypotenuse R, okay? And we know this is the geometry in meters of the side lengths of that triangle for state 1. So R is the square root of the two side lengths of the triangle squared and added together, giving us R is this, okay? So that was this length here, okay? All right, so in state 2, the rope is simply 225 millimeters, which is 0.225 meters, right? So the change in rope length between slider A and B, okay, from state 1 to 2, so state 1 to state 2, is 0.225, which is the final, minus 0.503, which is the initial. So the rope between A to B has shrunk 0.278 meters, which is basically saying that the rope on this side has moved equal and opposite to that, right? It's elongated on the other side of that pulley by 0.278 meters, right? So that's going to be our displacement S. Okay, so now we've got energy conservation, and we can basically break down, we can write out all of the formulas, right? And now it's just a matter of plugging in what we know. So we know that the dude was pulling on the rope with 200 newtons of force, and the displacement is how much the rope moved, right? the mass of the slider, actually wait, let's not write that in. First, we need to think about velocity, okay, between the two states. So from state 2 to state 1. So at the start, the collar is not moving, right? So velocity of the collar in state 1 is 0, right? What about in state 2? So velocity of the collar in state 2, what speed is it moving at? The answer is it's not moving, okay? So in state 2, we're analyzing a point in time when the collar is stopped moving, right? So both of these is just saying that the collar's not moving, it's staying still. So the idea is both of these are equal to 0, and therefore the whole term is nothing. So we don't have to think about kinetic energy because the kinetic energy in the first state and the second state are both 0. Okay, next is gravitational potential energy. So here's where we can plug in the collar's mass, so 7 kilograms multiplied by gravity. Okay, so delta H is the change in height, right, relative to some datum. So from A to, oh sorry, not A, okay. From 1 to 2, it increases in gravitational potential energy because it's moved up higher. Okay, so if it moves up higher, you've got a positive change of gravitational potential energy, and the amount of change is going to be 450 mil or 0.45 meters. Okay, so this is 0.45 meters. Okay, lastly, let's look at the term to do with spring potential energy. Okay, so we're interested in K, and so we want x2 and x1. So remember, x2 is the deviation from spring's equilibrium length in state 2, and x1 is the deviation in the spring's equilibrium length in state 1. Okay, so in state 1, this is state 1, right? In state 1, the spring is at its equilibrium length. Okay, so the idea is that delta L1, which we're also going to call x1, is 0 because it is at its equilibrium length, okay? What about delta L2, which we're going to call x2, okay? What is its deviation in its equilibrium length? And the idea is that there's a formula for it, right? L2 is its length. Okay, this is almost like a more confusing way to say it, okay? But L2 is equal to L naught, oh, sorry. Okay, you know what? L2 is L naught minus the amount it's compressed, right? And what you can do is you can cancel these out and you basically get x2 is negative 0.75, right? That's one way you can do it, right? So what I'm trying to say is that this whole term gets replaced by this, and then you can cancel out LO, and you're just left with this term. Except that's probably a more confusing way to think about it, in my opinion. What you can do is you can just look at the spring and think, how much has the spring deviated from its equilibrium position? In other words, how much has it compressed? And it tells you in the question already. It tells you that it has compressed 75 mil, which is negative 0.075 meters, okay? So negative meaning compression, right? Does that make sense? So if you got a negative x2 value, it just means that's how much it's compressed relative to its equilibrium length. Okay, anyway, so let's sub that in. X2, negative 0.75. X1, 0, because in X1, we haven't touched the spring at all. Okay, cool. So now that we've plugged in everything except for one algebraic value, k, which we're interested in, what we're going to do is we're just going to, because there's a lot of numbers, I find it easier to kind of pre-bake these numbers on my calculator. All right, so that's all of these, like so. And you can see that you're interested in working out k, right? So you just rearrange for k, and then you get k is equal to this. newtons per meter. Okay, so that's the spring stiffness, right? And you can work that out based on like all of the other energy terms. Does that make sense? Yeah. Okay, so I think we don't really have time for question 3, but I would still recommend that you try this out in your own time. It's in my solutions. It's a very similar question where it's to do with energy conservation, and it's to do with springs and pulleys and stuff like that. But instead of working out the spring stiffness K, this time we're working out P, which is the external force which is applied. But I think it's very similar to the previous question, so I'm going to skip it. Okay, the next topic I want to tell you guys about is impulse momentum. Okay, so probably the trickiest thing about impulse momentum is keeping track of the variable names. Okay, because here I've called momentum G. In the past, you might have seen it called P for momentum or something like that. But it's got the equation m times v, right? Impulse is your change in momentum, and in the past you might have seen this be called I, right? And even in the lectures it's probably called I, but I like to call it J. Okay, so yeah, so impulse is the change in momentum, and again we're going to need 2 reference points, right? So we're going to need 2 states of energy, which we're referring to, and it's the change between those 2 reference points in terms of its momentum. And then there's kind of 2 equivalent relationships that we can get from this, right? The first one is the force-time relationship, and the second one is the mass and velocity relationship. Okay, so that's going to help us solve a bunch of questions. Another thing to realize is basically you can think of conservation of momentum as you have some kind of initial momentum in your system, you add the change on, and then you get the final momentum. Okay. All right, another way you can think about it is when you have different objects and how you split up your momentum terms. Okay, so for example, if you've got 2 pool table balls that are hitting each other, they can collide elastically or inelastically. Okay, so I'll explain what that means before the next question. But you've got these 2 pool table balls and they're clashing against each other. The first state of energy you might be thinking about is when the velocities are pointed towards each other. And the second state of energy you might be thinking of is when, like, after the collision and when the velocities are pointed away from each other, right? So that's one scenario. Another scenario is a perfectly inelastic collision. So an example that they might give you is you've got 2 cars and they're like heading towards each other in the first state of energy. And in the second state of energy, they've collided and they get attached to each other, like they've glued together. And this is when they start moving together. Okay, and this is called a perfectly inelastic collision. And their masses get added together, and they have they share the same final velocity. Okay, so that's like, so say for example, the momentum results in the cars moving to the right altogether. Okay, so let's do a question. So here you've got some car and it's being towed by another car, and you've got this rope that's towing it at a decline of 60 degrees from the horizontal. So we know that this car is 1,200 kilos, and we're also told the initial velocity of this car and the final velocity of the car. In fact, the whole system, okay, because they're moving together. And this, and what I should say is that this is the car speeding up, right? So these are the cars moving together, and first state of energy, they're moving at 30 kilometers per hour. Second state of energy, they're moving at 70 kilometers per hour. And this change happens over 15 seconds. And we're told that the rolling friction, in other words, the kinetic friction, is 500 newtons. Okay, so that's the system's moving. This is the amount of friction that's applied overall, yeah, as like a flat number, right? Okay, so let's think of the car as a particle, like so. And this is the free body diagram of the car. And we're interested in the tension, right? T, which is unknown. And we do a very similar thing to, oh, well, actually, we actually don't care about what the normal force is in this particular question because we're already given the friction. So we don't need to actually directly work out the normal force. We're just interested in finding an expression for T. T is the tension in the rope. So we're going to take the horizontal equilibrium. Sorry, not equilibrium. We're going to take the horizontal directions equation of motion. And basically, it'll be like this, right? So we're looking at the horizontal component of tension. So that's T cosine 60. And we're going to subtract off the rolling friction. Okay, so this is the rolling friction. And this is going to be equal to MA. We're going to call MA F net. Okay, so this is the net force. Okay, so let's just call this F net. So we're saying the conservation of momentum is saying the momentum in the initial state plus the change in momentum is equal to the momentum in the final state, right? So let's plug in the things that we know. Okay, so we know that the mass is 1,200. We know the velocity. Oh, one more thing. Let me convert everything to SI units, okay? So if you've got a car that's moving at 30 kilometers per hour, this is the way I like to think about it, right? I always get confused as to whether you multiply by 3.6 or you divide by 3.6, right? When you're converting between kilometers per hour and meters per second. Okay, but if you think about it, if you're driving through a school zone, right, it's roughly 30 kilometers per hour, right? If you're driving through the school zone at, and I multiply this by 3.6, at over 100 meters per second, just think about that like physically for a second. That makes no sense. It's extremely dangerous. So that means that if you wanted to convert between kilometers per hour to meters per second, it's actually the other way around, right? You're going to divide by 3.6. Okay, that's one handy way, like rule of thumb that I like to think about it in terms of. So we divide 30 by 3.6 and we get 8.33 meters per second, which sounds more reasonable, right? Similarly, we're going to divide 70 by 3.6 and we get 19.44 meters per second. Okay, so these are the actual values we're going to plug in. We can't plug these in because they're not in SI units, okay? So the SI unit version of V1 is 8.33, okay? And that's going to be there. All right, F net. So we have an expression for it, and that's this, right? So we write T cosine 60 degrees minus 500. Okay, so that, let me do that in a different color maybe. Oops, what's going on? So that is F net. Okay, and then delta T is the change in time, okay, between state 1 to 2. And we're told that this change in speed happens over 15 seconds, right? Okay, and then M stays the same, so 1,200. And then speed 2 is 19.44 meters per second. Okay, so if we rearrange for T, which is the only unknown at this point, we get 2,777.76 newtons. So now we actually have the tension in the rope. Okay, that's the tension in the rope. Any questions about that? Oh, fantastic. Cool. So let's talk about collisions. So this is a measure, sorry, the coefficient of restitution, E, is a measure of the elasticity of your collision, okay? So before your collision, let's say you've got two pool table balls and they're headed towards each other. After the collision, they're headed away from each other, right? So there's a relationship in terms of this value E, right? Which tells you how much of the speed of those two objects is conserved after the collision, right? So if you have an E value of 1, that's a perfectly elastic collision. That means that all of the momentum is conserved in that collision. if you have a inelastic, you know what, I don't know what I was thinking of the plastic thing. Let's call it inelastic rather than plastic. I think I was trolling before. Okay, so you've got an inelastic collision, and that's a range of values, right? That's when E is between 0 and 1, exclusive. Okay, and this just means part of the speed is conserved. Sorry, not speed. Momentum is conserved, right? After the collision. A perfectly inelastic collision is one where the objects end up getting glued together and moved together in the end, right? Okay, so I'll show you how this works in the context of a question, and usually it's used to give you an extra formula when you have two unknowns, right? So the idea is you're going to use conservation of momentum as one equation to help you figure out one potential unknown, and coefficient of restitution, this equation, is going to give you another equation. So you'll be solving two unknowns simultaneously. Okay. One more thing before we do the question is this is the idea that coefficient of restitution E only applies for the normal component of an impact. Okay, so what do I mean by that? Pretend you've got a paddle, a table tennis paddle, okay, and this is the side of it. And you've got a ping pong ball, and it hits this paddle, okay, and for whatever reason, sorry, and before we were talking about 1D collisions, right? 1D referring to these two objects only clashing on a straight line, whereas this is a 2D collision, right? So you've got an X component and a Y component, or rather, you can think of it in terms of normal and tangential. In other words, like relative surface direction to like the point of impact. Okay, so what do I mean by that? There's a normal and tangential component. So any force which is tangential to this impact surface is completely conserved, right? So 100% of the tangential component of that force carries over after the impact. However, if we've got a coefficient of restitution of, let's just say 0.5, that means that half of the normal force disappears after the impact. So what this would look like in terms of the arrows and the vectors is something like this. Okay, so the vertical component, or the tangential component in this case, is 100% conserved, and then 50% of that horizontal component is conserved after the impact, right? So this versus this. So this is 50% of the pre-impact horizontal force, or normal component. So that's what we're referring to when we say coefficient of restitution only applies for the normal component of the impact, right? Does that make sense? Kind of. Okay. Hopefully that will not come up in your test, because that is a bit of a more advanced component of it. Okay, so we're interested in finding the velocity of object A and B after their impact. So we don't really care what these objects actually are. Let's just say they're two boxes that hit each other. We're told the initial speed and the masses of both objects. And what we need to do is we have two unknowns, right? That's an unknown. And that's an unknown, right? And we have two equations to solve for these unknowns, right? The first equation is the coefficient of restitution, okay? We're told that the coefficient of restitution is 0.6. So 60% of the momentum is going to be conserved after the impact, right? So this is the formula for it, right? This is the literal formula. And we just plug in what we know, okay? So we know that the initial speed of A is 7, and the initial speed of B is -5. So it's -5 because our positive direction is going to be taken as going to the right, okay? In this particular question. So this one's +7, this one's -5, okay? And so this is like what it ends up being. And then if we rearrange for B2, right, because again, we have two unknowns, and we just need to rearrange for one of them. So let's rearrange for B2. So B2 is 7.2 plus A2. Okay. So here is going to be our first expression, which we're going to substitute in later. Now, the second thing we know is conservation of momentum formula. And this is going to give us our second equation. So we know the masses of everything. Oh, sorry, I've done it down here. Okay. So the masses, right, of everything, we're just going to plug in like so. It's 2 and 3, right? Okay, next is speed. The first object's moving at 7 meters per second to the right, and the second object's moving 5 meters per second to the left. Okay, and then we've got our unknowns again for their final speeds, right? Let's call that VB2 for the moment, okay? So that's VB2, that's VBA, that's VA2, VA2, yeah. We can substitute, instead of this green thing, we can just plug in all of this, oh sorry, this side, like so. Okay, so now we've substituted in equation 1. And what this allows us to do is, now we only have one unknown, right? So we've got this yellow unknown, and we can just rearrange it by grouping like terms, right? This tells us that VA2 is negative 4.5 meters per second, which means that it was actually moving 4.52 meters per second going left, okay? So that makes sense, right? Because after the collision, you'd expect that the box A moves to the left, right? And the amount that moves to the left is going to be 4.52 meters per second. Okay, and then after the collision, for B, you'd expect it to move to the right, yeah? So we're going to verify that by plugging it back into this equation. So the idea is, you've got this expression, right? You can just bring it back, right? And now that we know what VA2 is, right, we can just plug that into there and get an expression for VB2, which is the green one. So that's telling us that VB2 is 2.68 meters per second going to the right, which makes sense because you'd expect it to go to the right. Okay. Does that make sense for that question? So it's a simultaneous equation type question. Like, you may have seen it before already in the course. Okay, last question. So we're going to talk about force time graphs now in the context of this block, which has a linearly increasing amount of force that it's going to be pulled with, okay? So, and there's friction involved as well, okay? So there's a few things that's going on in this question, but I'll try to break it down. Okay, so the question says, the force P, which is applied to a 10 kilogram block initially at rest, varies linearly with time as indicated. Okay, so it provides you this graph. If the coefficient of static and kinetic friction between the block and the horizontal surface are 0.6 and 0.4 respectively, determine the velocity of block when t is equal to 4 seconds. Okay, so let's just visualize what's going on. You've got a box and it weighs 10 kilos, right? And it's being pulled, right, with a force of P. P is slowly increasing. So if I was to pull this box with my hand, for example, just my hand, I start by pulling with 0 newtons of force, right? So I'm just holding it, I'm not pulling it at all. And over 4 seconds, this increases to 100 newtons, okay? So what this means is, for example, at 2 seconds, I'm applying 50 newtons. Sorry, I'm applying 50 newtons of force, right? So this is just like me, like slowly increasing with more and more force, okay? So that's what's happening with force. Okay, the other thing you got to realize about this question is the system. So if you've got a block, right, like so, that's on a surface, and it's being pulled with P, right? And let's just say that it's moving, okay? We haven't checked that yet, but let's just say it's moving. You've got mg and you've got n. Okay, the thing is, we treat the vertical forces and the horizontal forces slightly differently, okay? If you looked at this and thought about it in terms of the forces which are applied, is the box moving up and down, okay? Or is it in equilibrium? Very good. So the idea is that vertically, our system's in equilibrium, right? The box isn't flying up and down. It's not moving up and down, right? Even if you had a rope that was pulling it, unless the rope was like being yanked and the box like literally comes off the ground, it will probably be in equilibrium anyway, vertically, okay? But horizontally, if our system's moving, which I still have to check, right, against the static friction threshold, that means that the box can be in equilibrium vertically, but in motion horizontally. Okay, does that make sense? So you have to treat these directions as differently. Okay, but with that said, we still have to do our due diligence in checking whether the box is moving or not. Okay, so the first thing we do is find normal force, right? Because we can't find friction without normal force, right? So we do the vertical equilibrium. And we find that since we know the mass of the box, okay, mass of the box is 10 kilos and gravity is 9.81, the normal force is going to be this in terms of newtons. Okay, so that's step one done. Okay, next, we have to assume the horizontal forces are static, right? And so this is 0. Okay, and the reason why we do this is we want to find out the max amount of static friction that we can, the max amount of friction that can be applied before the box starts moving. Okay, so we're interested in the static friction threshold. Okay, so again, static equilibrium. P is your linearly increasing force, and this is the static friction threshold, which is pointing to the left. Okay, it's opposing the motion. Mu s we're given as 0.6, and the normal force is 98.1, which we determined in the first step. So now we have P. So what this means is that at a pulling force of 58.86, this is the max amount of force that can be applied before the box starts moving. Okay. So on this graph, let's figure out what that looks like, right? So what they're saying is that over here at 58.86, that amount of force will cause the box to move, right? We're interested in finding out how long it takes before the box moves, because this is a straight line function, right? So we can find that out through using a straight line function, y equals mx plus b. Okay, so y-intercept b is 0, right? So we can just get rid of that part. What we're interested in is y equals mx, right? So the y-axis is p. We can figure out the gradient, and then the x-axis is t, right? So we're interested in the gradient m, okay? So m is just the rise of a run, and we have a point that is known, right? So it is 100 newtons over 4 seconds, right? That's what this point tells us, okay? Which is saying that the gradient is going to be 25 newtons per second. That's the increase of pulling force over time, right? Every second, it's going to increase by 25. So why this is important to us is now we can say P is equal to 25t is the equation of this line. Okay, so now we can plug in P and we can solve for t, right? So let me just write that again. P is 25t. We know what P is because we calculated it a second ago. And we can rearrange for t. So at time is equal to 2.3544 seconds, this is how long it takes before the box moves. Okay? Does that make sense? So that's how long before the box moves. Okay, so now the box is moving, right? So the rules have changed. Now we're dealing with the equation of motion, F is equal to ma, and there's going to be a constant rolling friction of Fk. So we can work out Fk, right? We're given that mu k is 0.4, and the normal force is 98.1, that stays the same, giving us 39.24 newtons, okay? So this is the rolling friction, okay? So P is going to change depending on at what point in time we're referring to, right? So the two kind of points in time we're interested in is at the very end, so at t is equal to 4 seconds, and the other one's at the point where the box starts moving, okay? So what this is saying is we know what P is, right? So we can plug P as 100 in to this expression, right? And we can plug P is equal to 58.86 into this expression, right? And in both cases, we subtract off the rolling friction of 39.24, and we're left with these two values. So these values is MA, in other words, is equal to F net, right? Which is graphed on the y-axis here. And so that value, these values can be plotted versus time, right? And this is our force time graph. And we're interested in the area underneath this curve, which is going to be the area of a trapezoid, right? So the area of a trapezoid, all right, and this is another tip that might help you throughout your degree. If you want the area of a trapezoid, there's a formula for it, but people usually forget it. Here's one way you can remember it, right? Here's a side length of A for the trapezoid, and here's a side length of B, right? And let's just say this is over L, right? If we want the area of this trapezoid, you might want this as like a helpful formula to remember it. What you do is you average the heights, right? You get the average between A to B, and you treat it like a box. So this area here, I shouldn't do it as X. The area is just the average height, right? And the way you get the average height is you get both side lengths and you divide it by 2, right? And then L is the base of this rectangle. Okay, so you just do average of the two heights which are different, it's two side lengths which are different, and then you multiply that by the length, right? So we're gonna do the same thing here. We'll go half, and so we're gonna average these two side lengths, right? 19.62 and 60.76. And we're going to multiply that by the length which it occurs, right? And in our question, sorry, I'm just making space. In our question, it's going to be 4 minus 2.35 is that length here, L, of our trapezoid. So that is all going to be equal to m times delta v, and that's just the impulse formula, right? We know what the mass is, it's 10, and we don't know what the final velocity is, but the initial velocity is 0 because the box was still at the start of the question. So all we need to do is solve for v2 now, since we know everything else, and we find that v2 is this. So now we've worked out the final velocity of the box after 4 seconds of pulling. Okay, any questions? Nope. Okay, thank you for coming. That's the end of my workshop.